is Dr. Gadji, and today is October 20th, 2017, and this is the lesson from partial differential equation of mathematical physics and integral equations. And lesson is small vibration of elastic string. So the first thing, let us consider we have a string stretched between two posts. So this is my two posts. The length of this string is A. And here we have x is equal to 0. This is the origin of this of the post. This left end point is the origin at x is equal to 0, and x is equal A is my second post, and the length of the string is given as capital letter A. The first, let us denote by rho a density function of the string. Density function of a string. If we take integral, if we take the integral of this density function over the length of L, we are getting the mass of the string. So in order to mathematically model this situation, this vibration, we have to make the following assumptions. The first assumption is the string is elastic and does not resist transformations. And the second assumption is the vibrations are small and the equilibrium position is on a point x and moves alongside a line that is perpendicular to the line connecting points at x is equal to 0 and x is equal A. This is two assumptions made. Next, let us construct the axis of U axis, and this U axis is perpendicular to the x-axis. And here what we have also one more option, that the strings of length is between 0 and A. When time t is elapsed, I'm going to put here time t elapsed. If time t is elapsed, then the equilibrium position at x will have a new position with reference to this u vertical axis. So we have a function x and t, u of x and t. Therefore, for the fixed time, we have a function u, which is u, x, and t, and this represents the shape of the string at the time of t. Next, let us denote by rho this subnotation of x, rho of x. This is the density of the string at the equilibrium position. At the equilibrium position. And then based on this function rho 0 of x, we can right, we can consider the function rho x of t, this density function, this is the density of the function at a time t. As the strings stretches, these densities will be different at the initial equilibrium point and density at the time of t. Let us consider next the interval x1 and x2. If we consider this interval x1 and xt, and if we get the integral over this density function, we can get the mass of the string. So the mass of the string is the integral x1 to x2 of rho of 0 of x dx, and this is equal to the integral x1 and x2 rho x of t multiplied with 1 u x derivative by x 2 x 2, and here we have with the exponent of 1/2 dx. So this integral represents the mass of the function between the x1 and x2 over the interval x1 and x2. So I can represent this situation by the following graph. I'm going to sketch this graph. This interval is x. This interval is x plus delta x. This is my string, and here what we have. This is the tangent line here at this point, and here what we have. We have here angle alpha x, and here what we have. We have here angle alpha x plus delta x, and this is my tangent line right here applied at this point. So this situation represents, if we take this integral over the interval x1 and x2, and the mass of this string can be represented by this integral at the equilibrium position and also the position x plus delta x. Next, the interval x1 and x2 is the arbitrary integral. Arbitrary integral. So the integrands, they are continuous. So therefore, the density function, the density rho is the density rho at rho with subnotation 0 can be expressed by this formula based on the continuity of this integrand. Rho is equal to rho multiplied with 1 plus u by x, derivative by x to the second, and here we have 1/2, exponent 1/2. And if we consider this equation, This equation simply expresses and represents the conservation of the mass. Conservation of the mass. Next, let us denote by T of X. This is the tension. The tension at the point at X. The forces, based on this diagram, the forces at the horizontal direction have to be balanced. So we can write Tx plus delta x with this subnotation multiplied with cosine alpha x plus delta x minus Tx cosine alpha x is equal to 0 for all x's. So that means this the tension function. This tension function must be balanced alongside the horizontal axis. So that's why I put here T with subnotation x plus delta x multiplied with cosine alpha x plus delta x minus Tx cosine alpha with subnotation x is equal to 0 for all x's. If we divide this equation by delta x and let divide by delta x and let delta x to approach to 0, then we can write as this partial derivative d over dx Tx cosine alpha x is equal to 0. So we have this differential equation. And also we can denote based on this Tx cosine alpha x, we can denote this by letter r, and this r is a constant. So based on this, we can say if this is a constant, then we can say that the T is the magnitude of the horizontal component of the tension of the string. So right now, based on this, I can write the following integral, which represents the momentum of the string, and this integral is the following. I'm going to put this as my step 7, 4, 5, 6, 7. This step is 8 actually. So we have the momentum integral. Momentum integral, I can put integral rho u t ds, and this equal to the integral, definite integral between the interval x and x plus delta x, rho density 1 plus u, this function, derivative of this function alongside x to the second, and here 1